Hello. Today I wanted to discuss with y'all a sequence that somebody brought to me in Foundations of Analysis tutoring. And they were told to give a sequence that is uh, bounded and convergent but not monotone. And so they gave me this sequence. And I think when they brought it, they probably meant like negative one half to the n, which would actually make sense. But they basically presented this sequence to me, and I was like, "Whoa, this is a weird sequence. It's not really well defined in R, obviously for even n." But we got into a long discussion about this sequence in the complex plane, and I think it's actually very very interesting. So I want to share that with you all today. So if I start looking at this sequence, negative 2 to the 1 over n, if you know anything about this, like the nth root of a number, you'll recognize that taking a function to the power of 1 over n, this is like a multiple valued function. And in order for it to take a single value, we need to take a specific branch of the log function. And we'll see that in a moment. But I'm actually going to treat it like a multiple valued function. So let's write out the form of negative 2 to the 1 over n. In complex numbers, this is exponential of 1 over n log negative 2. And then the log of negative 2 is, not that, 1 over n. Okay, log of negative 2, we have natural log of 2 plus I times the argument of negative 2, which is pi plus 2k pi. Okay, and if you're not familiar with this, you may want to kind of learn some basic like complex variables, take a course. I'm also going to do a course on complex variables at some point once we finish up chaos and PDEs. So now we can just break up this exponential into um, the the part that represents the angle, i.e. the imaginary exponent, and then the piece that represents the radius or the magnitude of the complex number. So let's do that. So we get exponential of 1 over n natural log of 2, exponential of I pi plus 2k pi over n. And here, so turns out this log function, um, obviously, so the angle, if I look at the angle and the argument of this exponent here, it only takes unique values from k within 0 to n minus 1. Because you'll notice if I plug in k is equal to n here, the ends will cancel, and I'm just going to be adding 2 pi to the angle, which isn't changing my number at all. So because of the 2 pi periodicity of the complex plane with respect to the argument of the imaginary exponent, we know that this number will only take n distinct values, and I could just restrict k to the set 0 going to n minus 1. Okay, and so this first term here, this is just the nth root of 2, excuse me, the nth root of 2, which is a well-defined sequence in the real numbers. And then here we have like e to the I pi plus 2k pi over n. And so what does this sequence actually look like? Well, if we just set k equals 0, okay? So if we set k equals 0, then we're going to get something that looks like this. So I'll rewrite the formula so y'all can see it. We have the nth root of 2 times exponential of I 2k plus 1 pi over n. Okay, so if I were to graph this thing, I would start out at k equals 0. I'll put k equals 0 in red here. I'm going to start out at just negative 2 when n is equal to 1. And then essentially the angle is going to go from pi, and then as we increase n to 2, it's going to become pi halves, and this is going to be the square root of 2 here. And then the angle is going to become pi thirds, so somewhere here. And this radius is going to be the cube root of 2. And so we're going to get something that looks like this, essentially. It's going to spiral in towards 0. And the radius is going to approach 1, right? So this radius will approach 1, and this angle will approach 0. And it's kind of going to rotate along here. But now if we look at the actual, like here's n equals 1, n equals 2, n equals 3, etc. If we allow k to take on all of its distinct values, excuse me. So let's let k range in that set 0 to n minus 1. Then it turns out that for n equals 1, we only have one root to the equation. For n equals 2, we have two roots here and here. Okay, because I can always add an angle of pi. For n equals 3, I'm allowed to add an angle of 2 pi thirds. And so I'm going to have, let's do n equals 3 in green here. I'm actually going to have 3 distinct roots, and it's going to kind of form a triangle. So this is my n equals third entry of my sequence. Then for n equals 4, I'm actually going to get 4 roots here. I'm going to have something that looks like a square. And essentially, as you can kind of follow the pattern here, what this sequence is doing, this negative 2 to the 1 over n, is it's a sequence of polygons in the complex plane of side length n, okay, or n minus, yeah, side length n. And essentially, these polygons, whenever we have an odd number of vertices, we're always going to have a vertex on the negative real axis because there will always be one real non-negative root. So if I'm going to have like a pentagon, so it looks kind of like this, and then a hexagon is going to be like this in the complex plane. And then the other thing that's happening in this sequence is we're approaching essentially a polygon that's dense on the unit circle, okay? Because this radius is decaying on the order of the nth root of 2, okay, which obviously goes to 1 as n approaches infinity. And so the radius of these polygons is going to be approaching 1. And so eventually we're going to get like, as n approaches infinity, this sequence is approaching a polygon that's dense on the unit circle in the complex plane. So super, super cool sequence. It's incredible kind of what complex numbers can do. And it turns out that if you change this negative 2 here, you're going to get that the initial polygons will be different. Say you change the magnitude of the negative 2 to be like negative 1,000. Then at first the polygons are going to be much, much larger. But then eventually in the limit of large enough n, you'll still collapse onto something dense in the unit circle. So yeah, I hope you enjoyed that. And maybe you should, experiment with this and see if you can come up with the same conclusions that I did. Have a nice day.